Can you go over it? No, I'm going to the second floor, 3 o'clock.
Oh, lab.
Lab, I gotta leave it right now. No, join us, oh, you can come to 3 o'clock, up there, the one round before Thanksgiving.
Well, what's going on now?
You can see, we're going to the other lab, the resin 3D printers, and the other 3D printer, and you can see the water jet thing, the scanner, and through the scanner, so I would cover those two.
Yeah.
These two are boring. You could just make other kids that, like with the next 3 weeks or so.
Well, I'm gonna go try and fix the micrometer and see what I cleaned out the
Well, yeah, it's handled out somehow.
well, and then he showed me all the epoxy on the bottom. I told him, I'm like, look, man, I've got a bunch of samples coming.
I don't know how you can get that out.
That's what I'm about to find out if he did. Yeah. And then, yeah, I guess it was his idea. Or he was attempted to use the coin. Yesterday.
I don't know how you. Those the ones that you want the small bench or the big?
That's good. Here.
Like the audience bench? Oh,
No. The laser.
oh.
That's what he.
I'm not that.
He was basically that's where I was like, oh, but Sean.
Well, did you see what I'm saying?
Well, actually, I need to train part.
I think you should get it working, right?
I mean, it'll be good once we figure out the
Uh,
calibration, because I've got a phone call with the guy, so me and him can work together through it. Because I think he's got a bunch of samples too.
But I think you should train him after it's calendar. Like walk your
Well, I'm always gonna, if he can be there and we can like figure it out, I think the more people that know how to troubleshoot it, the better,
the calibrating thing.
potentially.
I don't sit with James with it after.
It's either everything.
It would be really, I don't. Do it fun.
Okay, that's sort of the email.
About,
Requesting access to the polisher.
in his life. All right.
Further training.
That's one. That's all.
Tomorrow at 8:30.
AM.
Yeah.
Okay. I mean. I'm getting that now after.
Talking about those super info.
Yeah, we got at least 2 weeks on this chapter. It's a lot in here.
2 weeks.
Yeah, I mean, this week and next week. I mean, well, yeah, but this repeats in here because there's different books. Okay, so there's a bunch of books. There's our book. But then if you go down to heat capacity, there's a bunch of books in here. I guess there isn't. Books are down in books. Kittle. So any of the Kittle, there's 2 Kittle books that are basically on that Kittle. the Dove book is on heat capacity, both Dove books. And this is the other Kittle book. Or Kittel, I think is how you pronounce it. And the Hill book is on heat capacity. So 1, 2, 3, 4, I guess 5. There's 5 books plus our book. There's probably some other things in here. So there's a lot of places to look, and there's stuff on the internet. And the thing is, like, they're all a little bit different. Like, it's the same derivation of the Einstein equation and the Debye equation for heat capacity. So it's kind of confusing. But maybe if you work through one of them, like then you can kind of see where the other ones are coming from. It's pretty confusing. But it's not, and there's it's like it's just differential math, you know, but with exponentials. So so it's possible to do. It's just a little tedious. So let's see. So yeah, this Dulong Petit, the 3R molar heat capacity. So you divide the heat capacity by the number of moles, and you get 3R out of it. Right? So that's kind of like the thing everyone tries to hit. And then this has to go to zero at absolute zero. It's like 2 touch points. So, and then there's actually an in-between touch point. As this thing increases from that 0 at absolute zero, at the lowest point, it should follow this t to the 1/3. I mean, experimentally, it follows a t to the 1/3 dependence somewhere. This is kind of, well, let's see. This shows that. So the Debye function, which is the dash thing, follows a t to the 1/3 decay. So it matches near absolute zero, and the Einstein one doesn't. They look kind of the same. Like the Einstein is the original simple, and then this Debye one is kind of more complicated, and then it matches perfectly near absolute zero. So everything becomes like kind of looking at things in near absolute zero, the heat capacities. Anyway, the Debye one works equally well as the Einstein at high temperatures. So basically that's the one everybody uses. But the original function is this Einstein. They both have a characteristic temperature involved. So the Einstein is going to involve, so you have atoms, like an atom in a lattice. So it's subjected to like a spring constant, XYZ. So it's got 3 spring constants for every atom. And then, but it isn't influenced by the lattice. So it's like a free atom gas. It's got 3 springs attached to it. And it also isn't influenced by having another atom near it, which isn't how like vibrations work. Right? In other words, if you vibrate one atom, the other atom's going to vibrate. So they're coupled. Right. So you can't, so essentially that one, if you just consider in one dimension and one spring, then there's just one frequency. Right. So the Einstein, if you plot, this would be like, so frequent h nu is the energy, like the Planck's constant times the frequency is the energy. So if you plot versus frequency, and that spring, that vibrating atom with just one spring just has one energy to it. So this is the density of states. How many, kind of, you can normalize it, basically how many atoms that have that energy or that frequency on the Einstein model. So it's just like one frequency. The Debye model is like a little bit more complicated, and it allows interaction between neighboring atoms. And then you get this distribution that follows the Bose-Einstein. This is a Bose-Einstein distribution, this curve. So you have a distribution curve, and then you see considering a bunch of different frequencies for the atom because it's coupled to neighboring atoms. Right. So So the vibrations are how it stores heat. You know, it's the heat capacity is how the material is going to store heat. It's storing heat by vibrating the atoms. You're at some temperature, it's vibrating, raises the temperature, it vibrates more. Right? The amplitude of the vibration increases. So it's basically that's the picture of how this is going on. So the Einstein anyway, so you end up with two temperatures for this. Like for instance, for copper, the numbers are given here, like the Einstein temperature. So you can convert so if you have H nu divided by K, that ends up having units of T, because H nu over KT, H nu is energy, KT is energy, so H nu over KT is unitless. So H nu divided by K gives a temperature, right? So whatever frequency you pick here, multiplied by Planck's constant, 10 to the minus 34, whatever, and then divide by the gas constant, like 9.8, whatever, and then you'll get the number for this temperature. That frequency just directly gives you this temperature, this Einstein temperature. And the same, this kind of cutoff frequency for the Debye, that also gives you a temperature. So each one of these guys has a temperature associated with them, and they aren't the same temperature, because one is assuming the material has a single frequency and the other has this distribution, this Bose-Einstein distribution of frequencies. Right. So if you get that temperature, you can predict the heat capacity. Or it's one temperature gives you this whole curve, like the whole distribution curve for the heat capacity, how it changes with temperature. So the heat capacity should go to zero when the thermal motion stops at absolute zero. And it should reach Dulong Petit 3R, which is 25 on this scale, joule per Kelvin, when you reach some high temperature. Right. So the cutoff is like it's got to be 3R up here, and it's got to be 0 down here. And in this region here, T to the minus 3 is what you're looking for. And Einstein gives some complicated function for that part. It's not T to the minus 3 though. It's like T to the minus 2, T to the plus 2 times exponential divided by 1 exponential minus 1 squared, the function squared. So it's not T to the minus 3 here. Right. So meaning that if you look at this paper this week, oops, what's the questions? It's gonna be not many people are here today. I don't know what the day is, but so this is the Einstein function. Okay, it's an absolutely perfect fit for this thing, whatever the thing is. And then this is some other thing, aluminum, Al, cobalt, whatever, some alloy or intermetallic or something. Right? This is vanadium and aluminum. So this material supposedly makes cages. So you have this normal aluminum vanadium cluster, and then there's holes where aluminum atoms can sit. So they can sit in a place where they're confined by a lattice. So they have these 3 spring constants, but they aren't part of the lattice. So they're actually an ideal Einstein material. They're just floating there and they can vibrate. So it's exactly what what Einstein was talking about. So it fits his equation perfectly. Right? His equation plus there's an electronic contribution too. So the electrons, so like in a conductor, the electrons are in a valence state, and then there's some in the conduction state. So there's a Fermi energy for the electrons, and some are above and some are below. That's the average energy. And if they're out of the valence state, they're in the conduction bands where they're just free electrons moving around. Those things are the Drude models in electron gas, right? And we know that gas has heat capacity, like the original equations are all the gas heat capacity things. This thing also has a heat capacity. And it turns out it's just this adds to the heat capacity, just temperature to the power 1 after a bunch of math. Right. So you'll see so if you're at low temperature, you should have T to the 3 and then plus gamma times T to the 1. And the gamma you can calculate, or you can look it up on a table. So it's only going to be things that are metallic conductors that are going to have are gonna have, here, so this is a table, it gives the Dubai temperature, it doesn't give the Einstein temperature, unfortunately, but gives a Dubai temperature, and you can see it varies quite a bit. And then it's got these numbers at the bottom are this gamma, this thing, this magneto. Let's see. It's called the coefficient of electrical heat capacity or something like that. Actually, I had that written down here. Maybe this is in the same version. It seems like, but it's like called the, oh, maybe it says up here, heat capacity coefficient. Right, so basically you'd add that in to get, and this, you would only use this because it's T to the cube. So like if you're at normal temperatures, T to the cube is much larger than, it's in Kelvin, right? So it's like going to be 400 cubed versus 400. That's going to be significantly, you can forget about that. Let me see this. If you're like tooling around like 10K, something, you'd have to have some special machine to get that, right? For some kind of super cryostat or so. Anyway, so that thing comes into play if you're in the game of like superconductivity, where you try to cool things down to get superconductivity, right? So it turns out this thing about the aluminum sitting in a cage, whatever this thing is. So superconductivity happens when you have something that has electrons that are free, like conductive electrons, but they aren't influenced by a lattice. Like in copper, you have the atoms are regularly arranged, and that lattice has a big modulus, right? So basically that kind of modulus kind of holds the electrons so that they remain independent electrons. To get superconductivity, you need to have what's called Cooper pairs. The electrons have to associate with each other so that, and somehow magically that becomes a superconductor. But if you have a lattice, that interferes with the two electrons supposedly share a phonon somehow. I don't know how, but somehow, a phonon meaning a vibration, and then they couple together, and then that thing will be a superconductor then. That's the theory, the B something, BMT theory for superconductivity. You know? Anyway, so the idea is like, if you could have a metal that was a conductor, like aluminum, which is in this paper, and then if you could have it so that it didn't have a lattice constraining the electrons, but still had the Fermi level and electrons in the conduction band, then they could pair up and they could make a superconductor. So that sounds like a pretty sweet deal. Like you have this thing all set up. Not only is it a perfect Einstein heat capacity machine, but also like it's got some potential to make like a superconductor with it by that route, you know. So anyway, so that means someone's going to write a paper about that. So they did. There's a couple papers. One is this, oh, that's crystal structure. There's actually a few papers following in line. This isn't a popular material or anything, but basically it's there, you know, and there aren't that many things that are perfect. Einstein crystal structure. It says Kelmkutz from Poland, I think. From Karlsruhe, right? Good place in Germany for science. And then Gdansk, must be nature science, natural sciences, Naturalistik. It's almost like German, Wissenschaft in German. I'm reading German Polish, so there it is, Poland. Anyway, so they figure out like this same material, this VAAL10, and they add in a little bit. 0.1 AL means fills the holes, these free holes, and then like they can make superconductors with it. So it means if you measure the resistivity, boom, it goes to zero, like at some temperature. So this is called a dirty superconductor type 2, because it's got a kind of a gradient here and not such a sharp transition, I guess. And you can tell it's a superconductor because if you put a magnetic field on it, it shifts it. That makes things worse. It makes it not as good of a superconductor. Or does something to it. Yeah, I think the bottom one here is the triangle high magnetic field. So magnetic field interferes with this Cooper pair formation. And if you put a magnetic field on it, it makes it less, drops the superconductivity transition temperature down. All right, so it's pretty low. It's like 2 Kelvin. That's pretty cold. Right, so it's, anyway, so that's kind of what's part of what's going on in this paper. This thing is to, anyway, this is where that thing, and then they also plot like the nuances of the heat capacity when they, I don't know, go through this business at really low temperature. In other words, a peak in the heat, in other words, if this is like a DSC and we're running heat capacity versus temperature, it's a dq dt, d capital T temperature, right, is the heat capacity. So if you plot that versus temperature, a peak in is the enthalpy, like you get a spike for first order transition. So when you see CP versus temperature and you see a peak, then that's like measuring a transition, and the transition is this superconductor transition, which supposedly only see first order when it's under a magnetic field. When it's not under a magnetic field, it's not supposed to have a first order transition. It's supposed to be a second order transition. So Donglu Shi in the department, used to be the head of the department. I think he published something like 300 papers in superconductivity. Then he just like, the field kind of collapsed, like there wasn't any money in it anymore. So he's totally stopped doing that. It's kind of weird. Like probably if you ask him, he can give much better description of superconductivity than I could ever, than the plastics guy can, but basically there are people in the department who are like world-renowned expert. He's a world-renowned expert in superconductivity, just doesn't do it anymore. The only business money in doing superconductivity now, and it isn't much, is to do like engineering of existing materials to make wires so that for like long distance transmission, electrical transmission, for high temperature superconductors. But I think that that's not even, right now what people are looking at is DC, high voltage DC transmission, and they aren't looking at superconductors, I don't think, that for that, like intercontinental transmission cables are high voltage DC, like kind of almost a megawatt voltage, megavolt transmission lines. Because when you have that kind of voltage, you don't need much current, like a very small amount of current. So there's not much loss. The loss is I squared. If you have no current, then you can transmit almost with no loss if you get the voltage high enough. And at that point, DC is better than AC. So anyway, given that, there's absolutely no money in superconductors now, which explains 400 papers going to zero, So cash seems to have something to do with it. Anyway, there is this paper from Los Alamos. So PRL is a good, or let's see, Journal of Physics Condensed Matter. It's a good journal. But there's a PRL in here on the same thing somewhere. I don't know. It's another trip down, like looking at different subjects. Some other group. This is a Japanese group kind of doing the same thing with superconductivity. And these guys, what other papers are on this? Oh, crystal structure. Actually, I didn't mention that one in the homework. It's the same group, this Polish people, but it's got much better graphics in it about what that aluminum cage looks like. That they do diffraction to show that it's there. It's kind of an interesting related paper, and it's got nice graphics. That's the main thing. It's got nice color graphics in it. It's probably a good study in how to make some of those pretty dry, like exciting. Yeah, this paper. I mean, I know what it's in. Journal of Solid State Chemistry. Those are all like they're good journals, both of those. Then let's see. So anyway, this is the Einstein function. So I wanted to kind of derive that today to get this equation, the bottom equation. And that's the question on the homework, is like derive that. Derive his equation 1. So the first, like equation 1, the first part, this thing is just that the electron contribution at very low temperatures, right? The second term is from that. So that's the gamma is the, whatever I said it was, the coefficient of electron, whatever the heat capacity electron coefficient. That's what it is. So, and you can look that up in a table, and it varies. The weaker the bonds and the material, the more conductive, the weaker the bonds, then you get higher gamma. That's how it works. So, and we'll go through that in some detail. The book goes through that gamma in some detail. So we'll go through that later on. And the other part is the Einstein heat capacity, which relies on that you have an atom. You have the metal atoms confined to a lattice, with the lattice is so they're basically free within the box. They're in a box, they're free, but they're confined by this kind of springs on the sides. And this aluminum acts just like this, basically exactly like that. So that's kind of the picture of things. So let's see what I got here. I did go through this entirely, like figure out exactly how to do it. Then I went to do it this morning. It's like, oh, I can't do it. Yeah. So hopefully I can pull something off. So you have, first off, like the frequencies, the modulus, right? I said that. So the square root of modulus by mass is a frequency if you have a vibrating. So harmonic oscillator is the topic here. So you have like spring, you have a spring. So like the force is the spring constant times the distance. So the further you pull it, the harder it gets to pull, right? And then the force, so the force times distance is energy. So the change in energy with distance is the force. So if you integrate that, you're going to get this square distance term for the energy. Right? Minus 1/2 kx squared is the energy for spring. And then the kinetic energy is 1/2 mv squared. Right. So in the force associated with this is mass times acceleration associated with the kinetic energy. So if you do a force balance that the potential and the kinetic equal each other, and then it's a differential equation which can be solved. We could propose a solution of a sine wave because you know the thing's going to spring back and forth, or you could solve the differential equation and find out the answer is a sine wave. So if you propose a solution like that, and then plug it in here, so you get sine here, and the second derivative, the first derivative is sines cosine, second derivative is going to be sine, so the sines cancel out. And then all you're left with is frequency in the spring constant and the mass. If you go through that, and you'll just get that the frequency is the square root of the modulus by the mass. Right. So this is the standard. So 1 over that would be like a time constant for this system. That was a relaxation time. So if you want to know if you have a viscoelastic material, then it's going to be the modulus, then you'll get basically kind of the same equation with the modulus and the viscosity in this thing. So basically, that means that if you know this Einstein frequency, there's kind of an Einstein modulus. So you can get from the heat capacity, which is going to be governed by this frequency, or the temperature, the Einstein temperature, you can directly relate that to the modulus of the material. So you can use heat capacity to predict the modulus, or you can predict modulus to predict the heat capacity. Right, so the things are coupled together through this kind of vibrating spring harmonic oscillator model. Right, so that's part of the picture, is to say that, because later on we just use that to get the modulus from the heat capacity. Other than that, I think there's nothing here of value right now. So then, there is something of value. So this whole thing means that if you have a spring, right, so it's got a natural frequency for the one. If you have a spring and a mass, it's got a natural, like a pendulum, so it's got a natural frequency to it, right? And the material is going to have this kind of characteristic frequency, right? And the energy is going to be related to that frequency, right? By if it's all right. So this is a real object, right? And then you have like quantum objects. So the quantum objects have this quantization of the energy. So in the case of so there's 2 cases here: quantum at the bottom, and then guitar string at the top, right? So the guitar string has has this frequency, the normal tone of it, whatever, it's a E tone or something. I mean, it's just coincidentally the first string on a guitar is an E, but so it's an E tone has an E energy, E1, right? So that, and then you're going to have overtones that are going to be like, the first overtone will be 2 times that energy, so half the frequency, because the frequency goes with the energy, right? So you'll have a higher frequency for the higher overtones, or it's a higher pitch. So if you hold the string at a certain point where the overtone happens, you get this really high pitch noise from it. And you can get different overtones. And N will be like 1, 2, 3, 4, 5, 6, up to infinity. Right. So there's all kinds of overtones. That's why when you string, it's not like a synthesizer when you pluck a string. You don't just get one single fixed frequency. Right? So anyway, I mean, the reason to say that is the same thing's going to happen with vibration of atoms in metals, and materials, and crystals, right? So you're going to have this kind of overtone effect. So anyway, the energy of that in a guitar string is the amplitude of how much you plucked it squared, then this frequency squared. So the energy doesn't follow h nu, it follows this thing for a real guitar string. So it follows a different equation because it's a guitar string, it's not a subatomic particle. Right? To solve for a subatomic particle, then you have to use quantum mechanics. You need the Schrodinger equation and talk about the particle as a wave and figure out what the solutions to the Schrodinger equation are, which are quantized. So there's fixed energies. Like this has fixed energies, that also has fixed energies. And the energy is going to be like n times h nu. So that's the frequency. If it's an angular frequency, in other words, it goes from 0 to 2 pi, then you normalize it by 2 pi. And then normally you get h bar would be h divided by 2 pi. And then this would be an angular frequency, like how fast it takes to kind of go in a circle, RPM type thing. Right. So anyway, there's two. All right. So all these equations seem to have at least 2, maybe 3, 4 different ways to write them. Right. So it's kind of important at first to figure out, at least get a rough idea. First be accepting that there could be different ways to write the things, and they can lead to different answers to the same equation. So you can have different functions that look different, but they're actually the same. Right. So that's the problem with this whole subject. So one thing is the energies in h nu, or it's going to be in h omega by 2 pi, or in h bar omega. Right. H over 2 pi is h bar. The h is Planck's constant. It has to do with how you relate frequency to energy for a subatomic particle. And that same equation works for any subatomic particle, like phonon, which is a lattice vibration, photon, any kind of particle beam, anything subatomic is going to be h nu, is the energy, because anything that has a dualistic wave particle nature. All right. So anyway, so it's pretty deep to get to just measure how something's, like when you heat it up, how much energy is going to take to heat it up. Like, but basically beyond Dulong Petit, you have to start talking about this kind of stuff. You know, so it's not pleasant, but basically it's there. You know? And if you don't do it now, you probably will never do it, and you probably won't. You'll run into it and you'll be like, oh, that's too hard to understand or something. And then, so that's not good. So basically it's possible to figure out a little bit of this. Anyway, so there's some kind of constraints on this whole system when it's quantum mechanical. So one thing, so there's certain rules, 1, 2, 3. So one rule is that at absolute zero, so the idea is like, if you had a frequency like this, so this thing goes to 1, the n goes 1, 2, 3, 4, right? Or yeah, so so basically, or this can be n is 0 and then you have 0 energy, right? So but there is no 0 energy, because if there was a 0 energy when you went to 1 Kelvin, like I showed you in the plot, the guy went to 1 Kelvin, right? And at that point, the motions would stop and matter would collapse into nothing. But we can go to 1 Kelvin or sub 1 Kelvin and matter doesn't collapse. Okay, so that's a fact that it doesn't collapse. That means that there has to be something else going on beyond thermal energy of atoms. Like there has to be something randomizing them. Right, so that's kind of rule number one, that things don't collapse. That means there's a ground state energy. So there's a 0 point energy that's 1/2 h nu. That means that when you write the energy, it should be h nu times 1/2 that takes care of the fact that things don't collapse when you get to absolute zero. Some kind of random thing, ill-described, I guess. And then plus n, which is the kind of the temperature part of the thing. Right, so n's the part, n is the order of the thing. So n in this case n starts from 1, in this case n starts from 0. And the 0 point would be like absolute 0, and then you have this ground state energy that keeps the world from collapsing as you approach absolute 0, which we know that it doesn't collapse. So that's one thing. Number two, there's something called the uncertainty principle, which says that you can't, for any kind of subatomic particle, you can't know what the momentum, there's the velocity times the velocity times the mass, right? So in other words, the velocity of the particle and its position, you can't know both of those. You can only know the position, or you can know the velocity, right? So at absolute 0, the velocity goes to 0, and then you know the position, so you would know both. So it would break the Heisenberg principle, which would mean bad things would happen, like time wouldn't exist or something, so a lot of bad things would happen if that didn't work. So it's basically, because of that, you need a ground state energy too. If you have ground state energy, then you still have uncertainty about where the stuff is, like the atoms and the position you don't know, or the velocity you don't know. Or you know the velocity, you don't know the position, or whatever. So you need this 0 point energy for that reason. And then the third thing is that you can measure it. Like you can measure this 0 point energy. Like in other words, the same as 1. Like in other words, things don't collapse. So because they don't collapse, you can measure the energy at absolute 0, what it would be. Because you could plot this as a function of temperature, you could find out what the 0 point energy is. So for those three reasons, this energy doesn't look like that. It looks like this. It's supposed to look like this. However, like a lot of times I'll just say E equals NH nu, and that's it. And they won't take this 1/2 in for whatever reason. And when you derive the equations, then you get a different answer if you don't have the 1/2, right? So you're going to take an exponential of this over KT. H nu 1/2 gives you like an exponential of H nu over 2 KT minus 2 KT minus H nu over 2 KT, and then that's going to be a prefactor to everything. That's a 0 state energy prefactor, right? So anyway, so those are a couple words to the wise, I guess. So this is the homework thing is like, what is it about this material, this aluminum inside cages, that makes it an Einstein heat capacity? And it's like free atoms confined in a box, harmonic oscillators in 3D, meaning if they're just perfect harmonic oscillators, it means there's no interference from the lattice, other lattice positions on that atom vibrating. So just a free vibrating kind of sphere with 3 springs attached to it, or 6 springs, like in the different directions, just vibrating there, thermally vibrating. Right? So that isn't real, but it's a simplification of the real, right? And then you have the energy of each mode or each quantum state. So there's fixed energies that it can take because it's a quantum particle. They're in mode n. So there's a 0th mode, which is a ground state, which would be H nu E 1/2. That's 1, 2, 3 to infinity. Right. So there's an infinite number of energy states it can take, but they're quantized. It's like step 1, 2, 3, 4. Right. Those modes. Anyway, so for that, you can calculate this sum of states, Zustan's summa, right? Sum of states. Zustan's of states, sum of states. So the Z. So that means it's going to be a Boltzmann factor for each one. So beta, which you'll see everyone use beta, is 1 over KT. It makes it kind of easier because you can do like derivative with respect to beta, and if beta's in the numerator, it's kind of a little bit easier to do the derivatives. That's the idea of that. But so anyway, so beta times the energy is a unitless number because beta is 1 over energy, 1 over KT. And then you can take beta times energy, which is going to be h nu times n times 1/2 plus n, and then you can get like you can substitute x for that thing. So you can just kind of rewrite this thing, plug in what En is, which is that 1/2 plus n times h nu e. And in this case, for the Einstein model, we're saying there's a one fixed energy. So for Debye, there's a spectrum of energies, and you can figure out by talking about phonons, which we'll do, what that spectrum looks like. But in this case, it's simpler than that. There's just one frequency. It's just one spring. And there's no interaction between the other atoms, so it's just a fixed number. You can just plug that in here. All right, so anyway, you get that expression. And then if you substitute in this x thing, this is kind of from it's kind of from there's a web page in the homework that that I listed, so this stuff is, so inside the homework, there's this thing, Valence, Tim, is Oxford, there's Einstein, Debye, PDF, and inside that, maybe I should open that, I guess, but you can take that to a certain extent, but it's not going to be the perfect answer of all, because you'll find out it doesn't exactly answer everything. And maybe there's some problems with it. That's not it. Where did it go? Note 9. Seemed like it wanted to open it. Crystal super da da da. 1, 2. This one? That one? This one? Oh no, because it's a PDF file. Oh yeah, no, this is it. All right. Yeah, so he goes through. He's got, it's kind of taken from here, more or less. Like you can see it's pretty short, but again, this doesn't really solve your problems, you'll find out. Because he just does things, he doesn't explain exactly what's going on. And he does the Debye. I mean, it's nice because it's short, it's just one paragraph. And then he does a free electron model, which he also doesn't really explain anything. So it's here, but it isn't. Anyway, it's here, it's pretty short and it should be understandable. It's kind of nice that it's short, right? So anyway, so that's there. That's a lot of this is kind of taken from that. So anyway, so yeah, you can plug that in and you can substitute this x beta h nu e, so that's x. And then the first term, so exponential of something times something, something times something becomes you can just pull out the other exponential. So you have exponential 1/2 of x beta nu e minus is just the prefactor. That's fixed, right? In other words, a half doesn't change with n. And it's a sum over n. Then you have beta nu e, which you say is x times n. And then the sum n to infinity. N is 0 to infinity. So it has to be 0 to infinity, which it is because you have ground state energy. And then there's this geometric progression thing. So you have x, sum of x to the n is 1 over n minus x if it goes to infinity, from 0 to infinity. If it's 1, you can put in another term and figure out how to get it to 0. But anyway, so that you can sub in and you just get this. So if you didn't have a ground state energy, then you get this Zustan summa is 1 over 1 minus e to the minus x. So you'll see that. You'll see that like over and over again. Zustan summa 1 over 1 minus e to the minus x. If you include the ground state energy, then you have this e to the minus x by 2 in the front, which is the 1/2. 1/2 h nu for the ground state from quantum mechanics. It's necessary because of the Heisenberg-Onsen principle thing. If you don't have that and it's 1 over that means that this x, that nu, it's assumed that nu already has that in it. Like it's been ignored because it's already in there. In other words, this thing is, he says then he says it's like E plus mu, and he says mu, in the electronic part, he says mu is the chemical potential. So that web page thing isn't exactly right. It isn't the chemical potential, it's a ground state energy. When he, whatever that thing was, he said it's this one? No. This one? No. This. Like when it gets down here, so this is another twist of this thing. I know it's kind of boring, but it's kind of like there's a lot to this. Like it gets confusing. Like he'll go down here someplace. So he has exponential beta E minus mu, and he says mu's the chemical potential, but it isn't. This is like the ground state energy. It's like, see, people will just, so you'll see that expression over and over again too. I'm pretty sure he's got that wrong here. Like that isn't, mu is the ground state energy. There isn't any chemical potential in this thing. Like there's no chemical potential. Chemical potential is of a thing in a phase, right? I mean, it's not appropriate here. Mu is the chemical potential. It's a symbol for it, but in this case, it's the ground state energy. So anyway, so it is pretty confusing. Like, so anyway, so you can either have 1 over 1 minus E minus X, or you can have this prefactor that's the ground state energy in this Z. The reason to say that is that Z is the ruling thing here. Like you can do, so for instance, Ni molecules at EI, energy is going to be the sum of Ni times EI. Boltzmann probability gives Ni is E to the, so the Boltzmann energy over KT gives the probability times N, and then normalized by the Zusammen sum, Z, right? So, and then the sum of those gives you the energy of the I state. So the probability of the I state times the number divided by the normalizing factor gives you the number of molecules at EI, right? And that's kind of how it's standard. Like anything you want to know the value at that state, then you just use that function, right? So then you have this thing's just defined there. And again, like, so, and then E is going to be N times Ni. So the sum of EI times N over Z gives the energy of the system. And then if you write that expression that way, then you can realize that the derivative of EI is this. So derivative of exponential is exponential times the derivative of the argument. So the argument's negative EI KT, put a negative in, but it's 1 over K, so it's minus 1 over T squared. So the minus minus gives plus. Now EI over KT squared is the derivative of that thing. If you compare that back with this argument to get the average energy, you have EI times that as that thing. So if you multiply by KT squared times N over Z, then you get that this thing dt of that thing is basically dz, and then dz divided by z gives ln of z, right? And so you can get that the energy of the system is just a log of this partition function, which is just the normalizing factor. It's not anything of any importance. It's like just to get the probabilities to work out, you sum up all the energy states, sum up all the probabilities so that the ratio would equal 1 if you summed, right? So it's just a normalizing factor. But it turns out log of that normalizing factor is the energy of the system, right? That's the free energy, the Helmholtz free energy for the system. So this Z thing, even though it seems totally insignificant, it's just a normalizing factor, becomes the main topic. Like getting that partition function is the main way that you get the energy for the system. If you want to know what's going on, you need to know that thing. So that's really, in other words, that energy is going to give you H nu for the vibrations, right? So anyway, going back to this thing, that's why the Z thing's important, how it's kind of framed up. Right? So you'll see this Z is 1 over 1 minus E, whatever. That's like a common way people talk about it. This is the right way if you include the zero ground state energy in it. So if you somehow include that in the energy, then you would get that. So that's why there's 2 forms, as far as I can see. Right. So anyway, so this is kind of the same thing. The energy, so the average internal energy, which is the average energy, is going to be the energy of each of the n states, which is going to be En is H nu times 1/2 plus n, this thing, times the x, which is our beta H nu, the probability function, and then n times that, n H nu E gives the energy of the state E to the n, or gives the probability of the state E to the n. So the energy of the state, like this could be En up here divided by KT, or beta En be the same thing as this NX thing, right? So anyway, so it's written this way because X is going to be, it's written this way because X has beta in it, and betas, we're doing derivative with respect to beta. So X is beta H nu E. So you don't write just En here, you write X because X has beta in it. So the derivative of X with beta is H nu E. Anyway, so this this thing normalized, sum of that over Z to normalize it, gives you the average energy of the system. Right. So, and then this can be rewritten as this by that same argument that I just gave about how to calculate the average energy. You're going to get, oops. So anyway, this expression can be written as this dz over d beta. You can figure it out if where dz, wherever z is defined here, if you take derivative of that, and then you can find out that this thing is dz d beta over z, which is d ln z over d beta. And then you plug in, so this you have to do yourself. So in the homework, I want you to do that, like actually go through these things, because me doing that here is going to take a really long time. I don't think you get anything from it at all. Not that you're getting anything from this, but you know, it's kind of like, in order to get anything from this, you have to just do it yourself and like actually work through the math of it. I mean, the only main math tool you need is that derivative of exponential is exponential times the derivative of the argument of the exponential. And that can go on and on. You keep doing the derivatives of everything, right? Until it finally gets to the last thing you want, which is beta here. Right. So I mean, you just have to do that. You have to do this derivative to make that work. So if you take log of this expression, so it's log of the top, log of the numerator minus log of the denominator, right? And then log of E is minus x over 2. And then log of this thing, there's a way to get that. The other thing you can do is that derivative of log, it's the same thing as derivative of x divided by x. The d ln x is the same thing as dx over x. So you can substitute d ln of this for d of this divided by this, divided by 1 minus e minus x. So you can see there's going to be a lot of terms in this. Right? The derivative of exponential is simple, or the log of exponential is simple, but the log of this thing isn't, because this thing, so it'll be the log of the derivative of this divided by this. So I think that'll help it out. Because the derivative of this is going to be just e to the x, derivative of x. So that you can do a log of, and then you subtract off the other one. So you can do that. You can figure out the sequence of that and get the answer to it. It's a mathematical, kind of a tedious mathematical thing. Anyway, this thing, if you do it, will give you basically this answer, which doesn't look, so the Einstein is going to be this thing over here, right? So we have like this thing. So the trick here is that if you have e to the minus x, you divide by e to the minus x, you get 1, and then here you get, and you divide here by e to the minus x. So this thing becomes 1 because it's also e to the minus x. So it's 1 over e to the minus x minus 1, and 1 over e to the minus x is e to the x. The negative makes it flip over. So you end up with positive e to the x, and then the h nu e's like there. So that gives you the average energy. So you can see there's a lot of math in this. I mean, I haven't gone through each step. Basically, I did do it at home. It's possible to do it, and you can get that answer if you do those tricks. Like you have to do this thing about realize that, oh, e to the minus x, you have to divide by e to the minus x to make that 1. If you know the answer, then you can get the answer. If you don't know the answer, you would never get it, right? So it's that kind of things. And then 1 over e to the minus x becomes e to the minus x, and e to the minus x over e to the minus x is 1. So you get that thing minus 1, right? And then if you do the derivative of that with respect to temperature, so the only temperature term is this exponential term down here. So this h nu e is just a lead term, h nu e. Right? So I had a problem with superscripts here, but anyway, so So you have H nu E is the lead term. That's not going to be affected. And you have 1 over this thing. Well, the derivative of 1 over the thing is going to be the thing squared. 1 over the thing squared. And then it's going to be negative. And you'll have negative, then the derivative of this thing. Derivative of 1 is 0. Derivative of that thing is that thing. So its derivative of exponential is exponential times the derivative of the argument of it, which is hk over t. And then t becomes t squared minus 1 over t squared. So you have minus kills off the other minus, and you have 1 over t squared. Because you already had a new e, you already had an h, so you have h nu e squared. The only problem is you have this k term squared, which you didn't have any k here, so you have to add in a k here, which is convenient because you want the Dulong Petit answer to be 3r. This is 1d so far, and I have k. So if I do 3d, it's going to be 3k times the number of moles, that's 3r, that's the Dulong Petit answer. So having this extra k is like the gift of math, that it shows up there. Then you have this square weird thing here. So the weird thing, so I guess Einstein figured out that weird thing could be more conveniently spoken of as a temperature. Then you could put it on a plot of like heat capacity versus temperature. So you can say like, here's this point that somehow governs like what the heat capacity is going to be. So that's what he did. He called that the Einstein temperature. I'm not sure he called it the Einstein temperature. That would be kind of, egotistical, I guess, but it's called the Einstein temperature anyway, this theta E. He probably just called it theta. And then everything becomes dependent on theta E, right? And then that's for 1D, 3D would be 3N to get it to R. 3, how many moles? This is heat capacity per mole, 3R. And then these other terms. So that's pretty sweet. It works. Like it works great. Like it matches up with this is ceramic aluminum silicate. Perfect, right? The only problem is like when you get near absolute zero, so like when you get near, this is copper. So when you get near absolute zero, there's kind of a twist, and some things aren't exactly perfect. So the stronger the lattice, the worse it's going to be, because the lattice, the idea is you have an atom that's completely free, like floating around in there, and it's got the 3 springs that are keeping it in the box, and that's it. But if the lattice gets to be like things that have a strong modulus, the lattice strength is going to be related to the modulus of the material. And in fact, the modulus is how hard it is to pull the lattice apart. So the higher the modulus, the worse the situation is going to be. It's something like mercury, where it doesn't have any lattice, or lead, where it's got really soft material, so the lattice is really weak. Those things are going to be like match it pretty well. When you get to like copper and iron and things where you have a strong lattice, then this thing's going to start to look funny, like it won't exactly match. So like copper, that's the match you get. It's still pretty good. And then it doesn't match at all down here. Even the dependence isn't right. So it's not following this T cubed, which is a strong signature at really low temperatures. You just plot T squared versus T, or C divided by T versus T squared. It's like a perfect straight line for almost everything when you get to really low temperature. So that's like people saw that when they started to get to low temperature, and they realized, like, I guess they plotted it every possible way. They found out that worked. They got a straight line. So they knew T cubed was what they wanted. That was known before Debye came along. Right, but still, so you have this function, somehow you got it. And that thing's pretty sweet. Like you can match the behavior heat capacity. I think that's 1910. It's like there wasn't much. I mean, before this came along, you said like, oh, it's 0, and I know it's 3R, and the rest of it, it's kind of like a decay curve. Maybe you could match it empirically with something. But then to have a theory that's based on springs in a box and have it match it perfectly is pretty sweet. And that's a sweet thing. That's a nice thing. It's like you have to feel you're not gonna get any money for it, but basically it's some kind of enjoyment involved in being able to do that, like to show how things are put together. Because not only that, but not only do you know heat capacity, but like how everything's put together. Like how is it, what is thermodynamics of a material? Like what is it? This tells you exactly how it works. Like you have a collection of all these atoms all together, they're in a crystal, then like they're vibrating. So in a gas is like free motion. So you have kinetic theory of gases and all, you can predict PVs, RT, all that business, but basically you get to metals and all of a sudden it's like, it's a different story. Like things are a lot more complicated. You have a lattice and who knows what's going on. They aren't free. Why do they still have a heat capacity at all, you know? And then all of a sudden, some guy, some joker in Germany or wherever, Switzerland, can come along and say, like, there's these spring things, like just simple springs, just put a spring in, that's it. And like, boom, I can predict the behavior of this. I can also predict the modulus from my magic temperature, you know? So it's like, pull this out of my hat and I can give you the modulus of the material. And I can predict the conductivity of it. Electrical conductivity, I can predict everything. Like, I know exactly what this stuff is, right? So it's more than just predicting the heat capacity. He knew like what the stuff was, and no one knew that before, right? So, and with such a simple model, like such a like almost stupid simple model. So anyway, so that's the beauty of it. It is a lot of derivatives of exponentials that is said, and you have to be able to manipulate. So maybe if you work together in a group, you can do that, or maybe one of you can figure out how to do it. If you want to ask whoever you think is the best at math, ask them and try to get them to figure it out. You know, I think it'll be a little struggle here to do that. Yeah, the electronic for this point is just, you can read about it. You know, I'm going to go through it in detail later on. So basically this T dependence is just added to the heat capacity. And it has to, I think I talked a little bit about how that works. So yeah, a lot of these notes are just from different books, how they do the same thing from different books. Let's see. Let me go back to when it does that. All right, that somehow it has to do that first. Like I hit escape to get out of the presentation mode, but it goes to the other thing first. So I want to go through this homework, whatever it says. So derive Kaplan's equation 1. Kaplan's equation 1 is just that equation, right? That thing we just did, same thing. So you'll see that equation over and over and over again. And then he shows this behavior, which is equation 1, which is the aluminum floating in the box. And then he sticks in this other one, which is the Debye. This is t to the 3, t to the t cubed. So he's plotting c by t versus t squared. If you multiply t by t squared, you get t cubed. It's a straight line. That's perfect Debye. And everything is perfect Debye except for this thing, which shows perfect Einstein. And so almost everything in the world is going to follow that. And you can see that this is t squared. So it goes 16 is 4 Kelvin, right? And then 9 is 3 Kelvin, and 4 is 2 Kelvin. So I guess 1 Kelvin is 1 here. So he's below 3 Kelvin in this plot. That's pretty cool. Right? And then he plots the resistivity, and he gives this equation. So this should be familiar to you, like at this point, like it's n over exponential there minus 1. That's just the Zusammen thing, right? That's a Zoom state, whatever, summe. So, which I pronounced wrong, but anyway, so that thing is just what this is the probability. It's a probability of a it's the energy level of the electrons in the system, or of the that gives you the resistivities proportional to the energy level of the electrons. So if you want to see a discussion of that thing, there's another paper in here somewhere. So it is like 3 or 4 papers. Oh, no, this guy doesn't talk about that. Crystal structure, no. Someplace in here, that's not it. Well, I can find it. I think I already opened it. But... electrical resistivity. So Cooper comes along. The other one was 73. This is 74. Cooper's at Yugoslavia somewhere. Downtown Yugoslavia, Zagreb, right? I only know Zagreb from the war they had there, right? Zagreb was like the bloodbath or something. So anyway, he goes through. He's talking about a correction. So the equation that the Cooper, or not Cooper, this guy's name Calpen or something. Calpen, yeah. So he shows this, it doesn't exactly match, like this straight line. And this t to the 4 thing is from the Debye theory, right? So it's not a perfect match here. So this guy gives a perfect match. He finds an equation for the perfect match for that. But he talks about the resistivity in this. Basically, so he has, this is the function that's given by Calpen, right? This beta h nu over 1 minus, which is just the formula, does not include, he explains why it's different. I mean, why it doesn't match it perfectly, because I forget what it is. Something about the interference of the electrons interfering with each other in conduction. But basically he says that this original equation is from just the probability, just the average energy of the it's just the average energy for the electrons in the system. And that's directly related to the conductivity. So he kind of explains it in here in the 74 or whatever paper. You might find somewhere else where they talk about, I mean, you might find just by Googling something else where they explain how does material display, why does it display Einstein? That's because it's basically this atom in a box now. The aluminum atoms, other than the matrix material, are just in a box. And then list the Einstein temperatures, compare it with like Kaplan. So Kaplan gives 22K, I think, or I think his Einstein temperature is 22K. 22K. And if you look up you can Google the Einstein temperatures for a bunch of different things, which I did. So they're here. So copper's 236, aluminum's 294, whatever. So lead has a lower because it's got a weak lattice. So things with strong lattice have a high, and weak lattice have a low. Right. So that's kind of the idea here. So you can kind of see, so this is copper, and copper is 244, is that right? 236. So you can see like where it is on this kind of decay curve. It's going to be like at the plateau almost. Like where it first starts the plateau, that's the Einstein temperature. It's like kind of around there. So I think if you look at Cooper, if you look at Cooper's thing, whatever that is, and he shows that same curve, isn't he? So he's got, let's see, resistivity versus, let's see, maybe this is the wrong guy. Einstein solid, this guy. So 22, so this is t squared, so 22 would be like 400 or something. Just kind of off scale here. Where this would plateau out, somewhere way over here somewhere, right, would be the, no, 22. Yeah, 22 on a t squared scale is 400. So yeah, it's way off scale. You can't see it. This is a log scale, but showing resistivity. So anyway, there's you can't see it on this plot, but in these generalized ones, it's kind of where it plateaus out. It's like over here somewhere, roughly, right? So yeah, so basically it's not like you would think it would be like, oh, the inflection point, like here would be some temperature, that's what I would think. If I guessed, I'd be like, the Einstein temperature is probably like 70 in this. Right? It's like way out here. So because the function is not an exponential, it's not like an exponential decay function where you get the relaxation time or something would be there. So anyway, that's how it works. So that's that. And then So his number's way lower. Why is it lower? So, oh, explain the difference. I did ask that. So his thing isn't, in other words, he's looking at these atoms, individual aluminum atoms that are confined in a box. It's a different geometry. So the higher temperatures because they're more confined in that lattice. Like the atoms in a copper lattice are confined by the lattice. They're fixed in their atomic positions, right? So there's a lot more constraint on them. So it's going to be a higher temperature to get them to move. Put it that way. Like, so motion of these aluminum atoms in their little box, they're gonna, and he even says in that paper, superconductivity paper, it's like rattling, they call it, rattling atoms. So they're just free to move around in the space. They're confined kind of by springs, but they're basically rattling in holes. And it's almost like you could shake the material and hear them rattle. So the temperature's rattling them. It's a really low temperature. 22 is 100, like 10 in order, more than an order of magnitude smaller than a normal material. It's like, where are you seeing this thing? Right. So it's kind of interesting, I guess. It's like it isn't any like an important paper, and it's not recent or anything, but there isn't that much. It's not many people, there's no money in looking at heat capacity. Like people aren't really looking at it, but it is. I mean, I'd say it's the most important thing from this course is to figure out like the Einstein and the Debye models. That's the thing you should take with it. Like if you ever teach this class, that's the thing you should teach. First thing is like that heat capacity models. Because that's kind of the basis of understanding how materials are put together. It was the first time anybody had any idea what was going on, put it that way. So then derive equation 2, which is the conductivity thing, which I'm not sure derive is just like, it basically is just the partition function. And it's just saying the average energy from the partition function. And then Cooper corrects his equation. I think you're going to have to read Cooper. I read it this morning and kind of looked at it, but I don't remember exactly what he does. It's something about the electron, the state of the electrons and how the electrons interact with each other and collide, and it deviates the function when you get to higher temperatures. Something like collision of electrons, and he can account for that. Somehow he can account for that in his equation. So you can kind of just see whatever you can get from this Cooper paper. It might not be that coherent, but anything would be good enough. And then bigger one shows that application of magnetic field can shift superconductivities. This is asking you to explain what superconductivity. This is type 2 dirty superconductivity, which he mentions a little bit in here. It's the same material. Let's see, this is a crystal structure. This is it's the same material that he had in the other paper. I think he might cite the other paper. And he's got the same issue. He's got aluminum atoms trapped in these cages. And then because they're so loosely held and they're conductive, so they're metallically conductive and they're loosely held, then it allows these Cooper pairs. It's kind of odd that this guy's name is Cooper, the guy doing the resistivity plots. And there's a thing called the Cooper pair, which is what defines superconductivity. It's a coincidence. I don't think it's the same Cooper. But anyway, it could be, but I don't think so. So anyway, and then basically that's why he's getting superconductivity in this, or why you'd even look for it in that. Because when you have a loosely bound, that's where it shows up. Loosely bound conductive electrons. Dependence. So the magnetic field interferes with the formation of the Cooper pair. So the Cooper pair, because the two electrons can share a phonon in order to do that. So they're naturally repulsive, but they become attractive because they share a phonon. And somehow the magnetic field interferes with that. So that I think is how, for a dirty superconductor, type 2 superconductor, that's how magnetic fields impact it. Like a typical demonstration of a superconductor is you put a magnet on the table. I think Dalushi does this in some class. Does he? Have you seen it?
Yeah.
Oh, and he pours like liquid nitrogen on it, and then he just puts it on and it just floats, right? So that's like a classic demonstration, right? So So the superconductor repels magnetic fields. So repelling it, it levitates, right? So anyway, so if you apply a magnetic field, it goes to figure that the thing is going to mess with its superconductivity. And that's what happens. Right. So it interferes with that Cooper pair formation. Did you take a class with him on this, or on, did he?
Material properties,
Oh, okay. All right.
electrical.
Yeah. Okay. That's good. So you must have said a lot about superconductors then. Oh, okay. That's good. All right. You must know more than I know about it. So you can answer E, like, well, just ask him, email him and say, like, oh, what the hell is this guy talking about? And like he'll be like, oh yeah, he'll talk an hour about it.
Yeah.
Just record it and transcribe it into the thing. It'll definitely be extra points. Anyway, so explain why it displays superconductivity and why the behavior is dependent on whatever. So just kind of fish around superconductivity a little bit. That's the idea of it. Anyway, so that's that business. Let's see what else. So the rest of this stuff is going to be about phonons. This is other books, there's other books and it's the same thing. Like the answer is the same. So you see there's missing here. And then the zero state energies in the bottom turn. Right. So basically the mu is the ground state energy. Like that's kind of what's going on here. Right. So the other thing in the web page where he says it's a chemical potential, it's kind of crazy. So anyway, the next thing is like to talk about phonons, like to go into some depth about, because you can't do the Debye part without the phonon thing. So the idea is like you have some atoms. This is from the wiki page on this, which I think you can get by clicking that link. But so you have atoms and they're so a sound wave or phonons coming in. It can be longitudinal, so like a compressive wave, right? Or it can be transverse, like what's shown here is a transverse wave, where it goes up and down. It's moving the things out of plane or something. So in other words, the distance between the atoms can change. Actually, the distance between the atoms is changing here too, but this is a transverse wave, right? So the idea is that, like, say you can put higher and higher frequency. So the atoms, so there's two size scales. There's this lattice spacing A, and there's this wavelength of whatever phonons coming in, right? So, but the atoms like translate any phonon of a higher frequency into this like fixed frequency, like the black line. So the red line's at a high frequency, the black line's the frequency that the atoms see. And the atoms see basically a lower frequency. So there's a cutoff, like when you go to higher and higher energy, but at the lower energy, there isn't, right? So at the lower, at the longer wavelengths, then there isn't a cutoff. So that means you need some kind of term that's going to be like, so usually the size scale is going to be this wave vector k, which is 1 over the frequency. So if you get to high, or 1 over the wavelength. So if you get to really short wavelengths, you can get large k, right? But short wavelengths are cut off because the atoms only respond at the A level. They're not going to respond at any shorter length scale because there's nothing shorter to respond. So you have this cutoff of A when lambda equals A, where k is 2 pi over A, and that's the fixed point where you're not going to have any response different than that. Right. So that means this k, so if you go to longer wavelength, then k gets smaller. So you have an inverse space situation. Like in other words, there's a cutoff at the large size where you don't go beyond that. Everything's going to repeat after that. And there's a cutoff and there's no cutoff at the small size. This k can just there's a cutoff at the small size, no cutoff at the large size. So k can go to 0. Like lambda could be infinity, and then k would be 0. Right. So Anyway, so that means you have this inverse space, which is similar to in diffraction, you have an inverse space too. You have Bragg's law kind of defines that you have the spacing of the thing, you end up with the angle that you measure at is inverse to the spacing. So this kind of inverse space connects mechanical deformation and diffraction together. So you both have a wave vector that's going to be inverse of the size, and they're both going to involve an inverse space description of things. Meaning, like when you look at an inverse, you can draw a picture of an inverse lattice. For diffraction, you can do the same thing for this kind of mechanical vibration of the thing. So the box that you have where you can get to A, where K is 2 pi over A, is called, and then everything can be smaller than that for larger wavelengths that affect the atoms differently. It's called a Brillouin zone. Right, so that's the way this thing works. You define this box thing, this Brillouin zone thing. So it's going to be basically like a lattice picture of things. The vibration is going to be described by a lattice, and everything's going to be in terms of this K vector. Right, and then K can the lattice will repeat. So you're not going to get larger K, smaller K will be larger wavelength. So everything that's within that box is repeated in space. Right, so the only thing you need to talk about is the one Brillouin zone. Everything else is described by that. Everything larger is within that box. Right, so yeah, that's kind of the idea of this thing. So so then you have this 0 point, right, which is like the infinite size thing, right, which would be like kind of like the mechanical, like the modulus of the object. If you're talking about a vibration, it's the size of the object. That's basically you're pulling on it. So that's the modulus. So you expect that at low wave vector, which would be really large sizes, that you'd get just the mechanical strength of the thing would come out of it. That's it. Right. So that's how it works. So you have basically at the 0 end of this wave vector, and you're going to get a straight line, and then the slope of that straight line will give you like basically the modulus from that equation. The thing we had when you had vibrations, and you're looking at just how kind of like how things vibrate. Right? So you get, this is kind of the picture for these acoustic phonons. So there's optical phonons and acoustic phonons. There's like two, so there's longitudinal and transverse. And there's optical and acoustic. So acoustic, I mean, so basically optical, I mean, they're like phonons you would see from interaction with light, basically. So when you get so from this phonon dispersion, you can get the density of states. So basically, this is called a phonon dispersion curve. So you have like the frequencies, like how many, what's the frequency, and then what's the wave vector. And then basically from that, you're going to get a density of states plot that's going to look like, for any material, it's going to be something like this, right? You have the 0. So these are just acoustic modes of vibration, and then one Brillouin zone, and then basically it goes to 0, and then you get the modulus kind of for each vibration, and then this transverse and longitudinal vibrations that are happening in the material, right? These are for the different lattice points. So because it's symmetric, you only need to have like half of a Brillouin zone to describe. So you have like the 111, 110, 100 longitudinal traverse dispersion relations, right? So this becomes, so you can see like this gets to become like really predicting how materials behave. Anyway, that's what we're going to do like next time. So kind of get into that. But you need that to get to the Debye model, which is going to be like based on that phonon dispersion idea. So anyway, so Einstein's pretty simple. Debye's kind of simple too. And also, so like the math of the Debye is stolen for other fields. It's like all these things, they're from metallurgy, and then the stuff gets stolen and applied to other things. You know, so it's kind of like, there's several reasons why it's important to know about the heat capacity. And one is that it's a basic understanding of the materials. The other is like, it's all that math is just borrowed and ported to other areas, you know. It's like all the what was it, heat transfer, and what's the other kind of transfer? Like all the equations are from heat transfer and then put into fluid flow or something. Right, so it's the same kind of thing here. Everything's just borrowed later on. Anyway, so why don't we quit there? Unless there's questions or anything. Email me, like you definitely will have questions in this, I think, on this thing. The superconductivity, you should just email Dalushi right today. What is this paper about? Be a good question. He can explain it to you. What is a dirty superconductor? Just ask him if he has any dirty superconductor magazines or something. I mean, he probably has some somewhere, you know.